You ask an AI agent to handle a complex server migration. It processes the prompt and outputs a flawless, multi-step proposal, exuding total confidence. It looks brilliant on screen. But the second you deploy it, the script hits a locked database, the model panics, and the system crashes. When this happens, our immediate reflex is to blame the AI. We assume the model lacks the parameter count or the baseline intelligence to finish the job. But the model is highly capable. It failed because it was pushed into a live environment without the explicit architectural scaffolding required to survive contact with real-world friction. This is the fluency trap. Because large language models are engineered to produce highly articulate text, they weaponize our own heuristics against us. We mistake eloquent prose for a validated execution plan. This diagram shows reasoning, the internal problem-solving process. The AI generates tokens in a complete vacuum, completely isolated from external reality. Planning is dynamic. It is the active sequencing of operations against a messy, unpredictable external environment that constantly pushes back. An AI relies on a static context window. No amount of training data will help it logically deduce that your specific payment database threw an unexpected error at this exact second. To bridge the gap between isolated logic and live execution, the system requires a mechanical control loop. If you ask an AI to solve a planning problem using only a reasoning scaffold, you force it to hallucinate a frictionless universe. In production, that guarantees a catastrophic collapse. The foundational engineering fix starts with decomposition. Instead of handing the model a massive, ambiguous prompt, you strictly bound the task into isolated sequential subgoals. Once broken down, the agent needs a way to interact with the live environment. That operational backbone is the react loop, reasoning and acting. It operates in a strict cycle. First, the system forms a discrete thought hypothesis. Then it fires a physical action to test that hypothesis against the world. Then comes the observation phase. The external environment reflects back raw results, feeding them directly into the AI to physically force an update to its internal state. This cycle neutralizes the fluency trap. It forces the AI to ground every token prediction in observable physical reality, rather than relying on its own statistical assumptions. Even with live tools, models suffer from autoregressive gravity. Earlier tokens exert a visible distortion field over the output. If the model hallucinates a fact, the statistical weight of those tokens forces the rest of the text to align with that flaw. This is why the standard practice of asking an AI to double-check its own work in the same window fails. It is statistically unable to escape its own gravitational pull. For high-stakes factual execution, the system requires an explicit circuit breaker called chain of verification, or COVE. COVE extracts discrete claims from the text. Then it spins up a completely fresh, sterile AI instance, scrubbed of the previous draft, and forces it to audit the facts independently. A localized hallucination can trigger an irreversible downstream disaster. To prevent that, verification must be executed as a strictly isolated mechanical step that is independent from the generation process. For exceptionally brittle multi-branching tasks, engineers can escalate to heavy artillery. Methods like self-consistency voting or language agent tree search allow an AI to systematically explore multiple paths. Look at the trade-off. Running redundant parallel reasoning paths inflicts a staggering compute penalty and instantly spikes your latency into the red. It is tempting to deploy these exotic, complex search trees as default starting points. But applying them to deterministic tasks burns time and money. We have to move away from treating AI as a magical bag of prompts. Building reliable agents means selecting from a strict, cost-aware architectural menu. True mastery of AI systems engineering is defined by restraint. Success is measured not by the complexity of the reasoning engine, but by deploying the absolute lightest architectural scaffold that reliably solves the task.